Okay, let's take a look at today's lesson. It's on concavity. So let's talk about that. First of all, we have let's look at the graph first so that we can see visually what concavity is. Notice here, if it's like cupped down, it's kind of, if you think of it as a cup and it's kind of upside down, cupped down, that's concave down. If it is up, cupped up, it's concave up. So visually that's what concavity looks like. A big important note here that some students perhaps maybe intuitively you realize, or maybe you don't, straight lines don't have any concavity. Alright, so if you have a straight line, it's not going to have concavity, and it kind of makes sense. We actually have a test for concavity which involves the second derivative, and if you have an equation of a line, you'll be able to get a decent first derivative, right? But the second derivative it's not going to be anything. So, lines don't have any concavity. So it's important to know, because if graphically, if you have a picture you're trying to judge concavity on, whether it's concave up or concave down, you need to recognize that if it's a line, it doesn't have any. Okay, so just so that you're aware. Let's look at the definition of concave up, concave down. This definition is actually, it's a great definition, but I don't use this definition to determine concavity, and I'm going to explain why. It's kind of difficult to determine quickly using the definition. What the definition says is that it's, first of all, it has to be differentiable. It's concave up on an open interval if the first derivative is increasing on the interval. Now, in order to read that off of a position function, that's not an easy task. It's not saying that the function is increasing. It's saying that the first derivative is. So here they've tried to, draw a picture of what that might look like. We're concave up if the first derivative is increasing as you go from left to right. This derivative would have maybe a little bit less than 1, and then you keep going up and see how the derivative values, the slopes of the tangents are getting larger. That's what this definition is trying to talk about, is that as you head up on a concave up, your first derivative is going to increase, or the slope is going to get steeper. Again, not very easy to see on a graph. And on concave down, we would look at the first derivative and it would be decreasing. So as we are headed up, here's my tangent line, and then there, notice the tangent lines are getting more and more shallow. So that's what the definition is referring to. It's a great definition, but I really don't use it to determine concavity. I think that's much more difficult to do it that way. What I like to do is use the test for concavity. And in order to do that, we have to have a twice differentiable function. Let's talk about what that means. That just means that you need to be able to take two derivatives of it. Twice differentiable means you take the first derivative and then you can take a second derivative. So yes and no. Sure, that's what, but to be able to see it, here we would have to see it visually when the derivative is increasing or decreasing. Here we're going to be able to tell it much easier. It's the same concept, it's just going to be easier to tell. So on this test for concavity, we want the function to be twice differentiable on the interval, whatever interval we're interested in. If the second derivative is positive on the interval, then the graph is going to be concave up. Pretty straightforward. We're doing a sign chart like we did yesterday. Yesterday we did a sign chart on the first derivative. Today we're going to be doing a sign chart on the second derivative. Much easier to determine signs of an interval rather than all of these slopes, whether they're increasing or decreasing. Does that make sense? If you want to do it this way, you are welcome to do it that way. But this test is much more straightforward. Okay? And then likewise, if we have the second derivative negative on the interval, then we're concave down. So that's our test for concavity. It involves the second derivative. Okay? All right. So let's take a look at this point of inflection. It's pretty important. Let's talk about what it is. Point of inflection, it says it has a tangent line. This kind of tripped up some people earlier today. Let me talk about what that means. What does it mean to have a tangent line? It's got to be differentiable, right? I mean, that's what it means to have a tangent line. So if it's not differentiable, then we won't have a tangent line. Okay? So we really don't run into this. We're not going to run into this on this test for concavity. Our sign chart is going to guide us the correct way. Okay, so this isn't going to be an issue for us. Of course, it has to have a tangent line because we've just said it has to be twice differentiable in the interval. So if it's twice differentiable in the interval, isn't it going to have tangent lines on the interval? Right? It's really a non-issue for us to worry about, is what I'm saying. If this is true, if it's twice differentiable in the interval, then it's going to have tangent lines on the interval. All right, it has that, and it's where concavity changes sign. It's where concavity changes. So in this particular picture, we're going from concave down to concave up. This is the function x cubed. And right here would be the point of inflection. It would be at 0, 0. It's where we change concavity from concave down to concave up, or vice versa. One important thing to note, if I have a straight line, and let's say this piece, a curved piece, is this going to be a point of inflection? No, because does this have any concavity? No, I'm not changing from concave up to concave down or concave down to concave up. I'm changing from no concavity to concave up, and that does not qualify as a point of inflection. Okay? So you're talking about something like this, and then, maybe there's a corner there. We would just have to look at it. We'd have to see, could we take the second derivative of it? Is it, is it going to be, is this function continuous? Can we take the second derivative? That kind of thing. And if we can, then, did we change concavity? Yeah. So we just have to look at it. All right. Other questions on the concepts? We just have a couple problems to do to demonstrate these concepts. So basically you have concave up and then concave up. You have a cusp. That's a cusp, right? No point of inflection because you're going from concave up to concave up. Okay, so are we clear on that? Okay. So let's take a look at a couple of examples to help us with these concepts. And you're going to see concavity on the test. I mean, it's just going to be there in some form or another. So all of these tests and things are important. What we're doing is we're bringing in yesterday's lesson, use the first and second derivatives of this function to determine intervals of increase-decrease and concavity. Also, they want us to find the inflection points and graph it. So they want us to do all of that stuff. All right, so let's work on that. First and second derivatives. So let's find our first derivative. Our first derivative is 3x squared minus 6x. Just as we learned yesterday, to find intervals of increase-decrease, we determine if there are any undefines. There aren't, right? No singular points. Stationary points we probably have. So we set it equal to 0. So x is 0 and x is 2. We do our number line, our sign chart, and then we test the signs. Now, I'm pretty sure and comfortable with the fact that everybody in here should be able to do a sign chart, so I'm not going to walk you through it like I did yesterday. Just going to write the signs up there. If you're having trouble doing a sign chart, then just check with me and I will help you. All right, so we have our sign chart. Now, reason I keep saying you test the signs in the function you got the sign chart from is because we're getting ready to do another sign chart. Right? We're going to do a sign chart on the second derivative. So we need to really understand where to check the signs. I got 0 and 2 from the first derivative. That's where I'm going to check the signs. I'm going to go to the first derivative to check and fill in my sign chart. I'm not going to go back to the position function, right? I'm not going to go to the second derivative. I'm going to go where I got my numbers from. So we need to be really clear about that. Now, which I did, I went here and I checked, and those are the proper signs. So for increase, So for intervals of increase, we're going from negative infinity to 0 and 2 to infinity, because, we remember that from yesterday, right? Because f prime of x is greater than 0. Our intervals of decrease are from 0 to 2, because f prime of x is less than 0. Okay, great. Just a review from yesterday. Right. Our next step to work on concavity is to find the second derivative. So we need to do that. So I'll just write that over here. Let's find the second derivative, which is going to be, 6x minus 6. Set it equal to 0. And I get just 1 point, a little baby sign chart. Sometimes, I know it's kind of strange, sometimes the second derivative sign chart is larger than the first derivative sign chart. Just depends. It doesn't always work like this. So I check my signs again. We'll be very cognizant of where we got the number from. We got this number from the second derivative, so we're going to use the second derivative to check our signs. And so we do that, and we get this. So according to our test for concavity, we are concave up from 1 to infinity, because, what does this test tell us? Because, what's our justification? Because the second derivative is greater than 0, and we're concave down from negative infinity to 1, because the second derivative is less than 0. Pretty straightforward. It's very similar, isn't it? Just like what we did yesterday, but with the second derivative. Inflection points. Do we have an inflection point? We do, because we have a change in concavity. We have a change in concavity. Now, it's asking for the point. So that's right, we have our x coordinate of the point. To get our y coordinate, where do we go? Do we go to the first derivative, second derivative, position? Position, we're wanting a position, right? A position of something. We go to the position function, to the actual function. So I take the 1 and I come up here and I sub it in, and I get my y value of -1. That's my inflection point. And why is it the inflection point? It's because the second derivative changed from negative to positive. Or you could just say change signs. You don't even have to say which way it changed, because it doesn't matter, right? As long as it changes, it's a point of inflection. Okay. What I would like for you to do is to get into the habit of writing the justification down. Many times they don't care about the justification of the inflection point. They're usually really concerned about justification on these other things, but it won't hurt. And it takes like 2 seconds to write it down, so it won't hurt. Okay? So now we're supposed to graph this and see if it's basically our findings are consistent. So let's see. We increase. We have an inflection point at 1, -1. So let's go ahead and graph that. Okay, there's inflection point. We really don't have any other points. We could easily get our y-intercept, right? That's pretty easy to get. It's 1, so I'm just to help me with the graph. So I'm supposed to be increasing from negative infinity to 0. So increasing, I'm coming up, increasing from negative infinity to 0, right? And then I'm supposed to decrease from 0 to 2. So there's, from yesterday we know there's a maximum there, right? It's a relative max. It's gonna come back down, and we're gonna decrease till we hit 2. So here's 2. So we go through there and keep decreasing. Then at 2, we're supposed to increase again. So we increase like that. So let's see our inflection point is right here. Now my graph is not that good, but hopefully you can see we're concave down right here. And then this is supposed to be where we change concavity. And so now we're concave up. So that matches what we have just discovered with calculus. Are we okay with that? Okay. All right, this last one is just really a visual thing. We're supposed to look at the graph and determine the signs of the first and second derivative. All right, so let's do that. This is the graph, and again, we got to make sure we're looking at the proper thing. This is just regular position graph, so this is the graph of f, and we are supposed to determine the signs of the first and second derivative. So we're pretty used to looking at the first derivative, right? How do we figure out the first derivative from a position graph? Just the slopes, right? So as we look at the slopes, we're looking up this way. All of those slopes between 0 and 3 are negative, right? So f prime of x is going to be less than 0 there. We all agree with that? Okay, it's going to be less than 0. So now haven't really had experience or much experience with reading concavity off of position, but we talked about it on that first slide. Remember the shape? The shape, if the shape is kind of up or the shape is kind of down, it kind of tells you what it is. In this particular case, what do you think we're going to be? Concave up, right? Because it's kind of up. It's cupped up. So if it's concave up, what is the sign of the second derivative? It's positive. So then our second derivative value would be greater than 0. And that's really all they're asking. They're just asking us to read the signs of the derivatives off of the graph, off of the position graph. Okay, we okay? Questions?